Hey guys, what's going on? Today we're going to be taking a look at one of my favorite algorithms. I was very excited to make this video. Isolation forest. We'll walk through what it is, how it works, how it compares to some other similar algorithms, and then we'll look at some code from a real use case that I put together that we use in our business. So very cool stuff on that front. Excited to give you guys a little bit of real world code that actually people find some value in and things like that. Um, but other than that, all the links will be down below for everything that we cover, as well as a link to our Discord. It is growing every day. People are joining. They're talking about the projects they're working on, the models they're building. People are helping each other. So I definitely recommend joining that. Hopefully, I'll see you over there. But other than that, let's get into it. So, isolation forest is an anomaly detection algorithm. Sometimes it's also called an outlier detection algorithm, focused really on finding these anomalies and outliers in a data set. One of the key benefits of it is that it's very efficient with a low memory use, which means that, as we look at data sets that are either growing in size in terms of rows or growing in size in terms of columns and dimensions, very applicable, very useful. Nowadays with the size of the data sets we look at, especially in production use cases, that's very important that we have that efficiency there. Kind of a general idea about the way it works is that it's based on the assumption that because anomalies are few and different from other data, they can be isolated using partitions. And so we will kind of look at how those partitions work, how we decide how to partition the data, and the way that that goes from there. As you could probably guess from the forest part of the name, this is a tree-based algorithm, similar to something like random forest or something like that. One of the nice parts about this algorithm compared to some of the other anomaly detection ones is that it's invariant to the choice of a distance metric, simply because it doesn't have one. It's a tree-based function. There is no distance metric to calculate. So that means, not as much, parameter tuning and stuff like that, or choosing distance algorithms, some of those things that you see. None of that, as when we look at the code, we'll see that. So that is very nice. It does allow people that are maybe more on the beginner side to use it pretty quickly because you don't need to spend time doing that. Let's take a look at some other stuff here. So how does it work? And you'll see that I put references to the resources I used. I do want to give those people some credit for the information they have already put out that I was able to use going through this process. But the algorithm consists in sub-splitting sub-samples of the data according to some attribute, feature, or column at random. So you will see that we choose the different columns at random. We choose where to split the data at random as well. You will see that as we kind of go through, but that is sort of how we start to partition this data into groups. The idea around this is that the rarer the observation, the more likely it is that a random split on some feature would put outliers alone in one branch of the tree. So you'll see that when we grow this tree, the goal is that those leaves have the outliers in them from doing the partition. And the fewer splits it takes, it will take to isolate an outlier observation like this. So just a little bit of a high level. We'll take a look at a little bit more there. Here is a nice GIF of how this actually works. You can see we do a split parallel to the X. We do a split parallel to the Y. We're just splitting the data. We haven't identified any outliers yet. We do another split parallel to the X, and do one more split parallel to the Y, and we actually do get an outlier. So that is sort of how our tree, you'll see the tree example, but you can see we keep doing these partitions until we do reach an outlier, which is, fairly nice and fairly efficient. So how it works, the algorithm selects a random dimension. In this example, and even in the code one, it's the x-axis. I just used 2 dimensions for our example, I think that's easier to visualize. I don't really want to try to visualize a bunch of, complex data there. So, we'll be looking at 2 dimensions as well. So associated with the x-axis and randomly splits the data along that dimension. So we can see we make a split, very nice. The 2 resulting subspaces from the random cut define their own subtree. In this example, the cut happens to separate a lone point from the remainder of the data set. First level of the resulting binary tree consists of 2 nodes, one which will consist of the subtree of points to the left of the initial cut and the other representing the single point on the right. So we made our cut, and now we have one group here to the left. We have in this instance, just a single point. That's not how that always goes, as we saw in the GIF from before. But this time we do actually just get 1 point. We do actually get that outlier, which is kind of nice. And we can represent this in a tree that has, each of them on each side. In the other node, so in that group of larger data, we choose a different starting split. This time, it doesn't isolate any points. As we saw before, this is a random split. So this time we don't get any. That is perfectly fine. We end up with a tree consisting of 2 nodes, one that contains the points to the left and the other one representing the points to the right, although we've already identified one of those as an outlier, so we can kind of ignore that one for now. As we mentioned before, these splits can occur along any dimension. Here we do another split, this time actually parallel to x instead of what we saw before. And we are able to keep splitting, and you'll notice that I didn't see it there. We would end up with an anomaly there from our partition. So once we sort of continue down those trees, we would end up with a split there. On average, an anomalous data point is going to be isolated in a bounding box at a smaller tree depth than other points. When, that makes sense, right? When you're sort of partitioning and going from there, you keep going down the tree that has more data points because you have to keep partitioning that. Once one of the sides has an anomaly, where you go, there's nothing to partition. So that's fairly straightforward idea that you are really, your tree kind of looks a little bit one-sided because especially if you get, like in this example, if you get an anomaly like right out of the gate, like if your first partition has just an anomaly and then everything else, you're just going to have a one-sided tree of it building on one side, which is kind of interesting. Yeah, so you always have your anomalies are going to be much higher up than the rest of the data points have to continue to be partitioned. When performing inference using a trained isolation forest model, this is a model that can be trained. The final anomaly score is reported as the average across scores reported by each individual decision tree. Cool. So we want to take a look here at an example. This is a toy data set provided by Scikit-Learn that runs a couple different outlier and anomaly detection algorithms on this same data set. And we can kind of take a look here and see what we have. The first thing you'll notice about isolation forest compared to a couple other ones. First, I do want to mention local outlier factor. It doesn't have a predict function. It's not a trained model. So we don't have bounded boxes. That's why it's color coded. I just want to point that out. There's nothing missing on that one. That's just how local outlier factor works. But anyways, one of the things that's kind of interesting about isolation forest, you probably see compared to some of the other ones. One, some of the functions that use, like Gaussian understanding, they learn in ellipse. So you'll notice that, like robust covariance, you always get this sort of ellipse function. It doesn't fit the data well. This data isn't Gaussian, so it doesn't split well in this specific instance. But with some of the other ones, I don't find that they are as tightly bound as isolation forest. I think one of the things that I really do like about isolation forest is because it's fine-tunable, and it's honestly very fine-tunable. It's easily fine-tunable. you can get a very tight grouping around what is a outlier and what isn't that you sometimes don't get with the other ones, which I really like. I do really like that. It does struggle a little bit with holes. I think that these holes for support vector machines are a little bit better, but support vector machines sort of across the board are just a bit too sensitive to outliers. I think they kind of grab things that are outliers that really aren't, just because it requires fine tuning. You know, that's just kind of the way support vector machines work. So yeah, I just think you get a nice tighter bound fit with that. I just don't think it grabs as many data points. I think it's very rigid, very constructed with what an outlier is, especially when you look at this one here, which I actually think localized outlier factor did a great job at. The other one's not as much, but you can see compared, the support vector machine ones compared to isolation forest, these are kind of a mess. I mean, these, I don't know. Like I don't, these points here should not be included in the non-anomaly set. Like, these should not be included. This shouldn't be included. You can see this is a much, much tighter bound around what is an anomaly, what isn't. Actually, the covariance actually does a good job with that one. That's pretty good. But that each of these different ones, you're gonna have a little bit different. Where does it rank compared to the other ones? But I just think isolation force across the board. I think these look really good. They look much better than this. They look much better than this. I just think, when you look at like all use cases, all types of data with different sample diversities and things like that, I just think it's the best one out of the box when you sort of look at all the options there. Let's see if I anything else I want to cover with that. This example is on Scikit-Learn, so you could look at it on your own, but just wanted to show how isolation forest outlines outliers compared to some of the other functions that are available as well. I think a good general idea is there might always be other functions that are better for a specific use case than isolation forest, but I personally believe, because of how easy it is to fine tune and just sort of the binary tree nature, that it's a really good option for every use case. Might not always be the best, depends on the fine tuning, depends on the use case, but I just think it's really good. It's a, with it being fine tunable, your ability to get bounds that are tighter is much easier to do and much better, in my opinion, especially what we'll see when we look at the example. So let's take a look at the example that I put together. This is a real use case from our business. This isn't one that I just made up or something like that, although the data is mocked. I didn't want to use real data for something like this. But just to kind of look at what the use case is, we have a data set, and I'll run this first one so you can see it. We have a data set of queries. These are chatbot or search style queries. You can see a couple examples from the data frames head. These are search style queries that we have that come in, and then we have a length of the query. That is the number of characters that go into it. What we use this outlier detection model to do is track user conversations in our chatbot apps. So we're able to track for anomalies and things like that with the way that users are using the bot, either for a fine-tuning use case, or maybe we're just curious and want to track what users are doing and see maybe if they're doing something bad or something like that. The actual model has much more than just query length, but this is a pretty good one considering it's integer data. It's fairly easy to use and visualize. But this is one of the metrics we do have built in. So query length, and then we're going to do a run here of another one we do. We like to track what words are used in the conversation as well. Once again, from a fine-tuning perspective, if you notice that maybe your model for one specific customer is performing poorly, maybe they've complained, something like that. You can do this as part of your analysis of what's going on. Maybe they're using their use case, their language, the way that they're doing it is just different from everyone else's. And then maybe you need to do some fine tuning on that specific domain or that specific topic or whatever they're doing. Understanding what nouns and things like that they're using is a good way to understand what that domain is that they are focused on. So it loaded this data frame up. It's small. It's just a little test one that I made. And then I ran this. I just used a spacey named entity model to recognize the nouns and proper nouns. I loaded the spacey model. For each query, I just run this function that runs the named entity model. If any, and then I just total up all of the entities that are nouns or proper nouns. That super simple prompt. Function. And now we have a data frame with queries, the query length, and the noun count. And what we're going to look for is anomalies in this sort of two-dimensional data set. So we want to find anomalies when both, the query length and the noun count exist, or maybe one is very highly an anomaly, one isn't. I think it's pretty easy to see when it's just one data point. I don't even know if you need, an algorithm to do that. But when you start getting into more and more dimensions with your data, having an algorithm does this is much easier than trying something else. Because you can imagine that complexity grows as your number of dimensions grows, similar to like embeddings and things like that. So we have got our data set. Let's run this. We're going to make our X our input, and then we are going to split it in a train and a test. Very nice. This data isn't labeled, which is one of the other nice things about this. It is an unsupervised algorithm, so you do not need to provide sort of a label of this is anomaly, this isn't, anomaly isn't, this isn't like a classification type setup. You can actually do that with isolation force if you have that data. I could split this with an X and then a Y, and I would just define whatever my Y variable is, and then it would learn that relationship instead, but it's not required, which is, like I said, very nice. So we split our X and our train and our test. These are just data frames. And now let's run the isolation forest. We'll see if they give us anything cool when we pull it up. No, there's nothing. I think if there's anything worth mentioning in here. Oh, I know what's worth mentioning. Contamination. I was probably going to get asked about this. Contamination is a variable that allows you to, and they might even mention it. Let's see if they mention it. Yeah, they do. Contamination is the amount of contamination in the data set, essentially the proportion of outliers in the data set. It's used when fitting to determine the threshold on the scores of the sample. Now, what you're probably going to ask me is, if I don't have a Y variable, how do I know what my contamination is, right? Like, I'm trying to ask the model to figure that out. And that's a good question. I believe what you should probably do is just set this to auto. It'll just use the contamination threshold that's outlined in the original paper. I can't remember off the top of my head what the original one is. It essentially is like an assumed value if you don't provide a Y. If you are providing a Y, if this data was labeled, you would want to provide what that number is, like what that percentage is of outliers. But if you are just providing an X, you don't have your Y, you probably just want to go with auto. I'm going to go with the 0.05, 5%. I think that's probably fine. But you probably do want to go with auto. I can't remember what the number is in the original paper. It might be around 5%. It's just an assumed value that the model tries to use from that point. Cool. Oh, yeah, it's 10%. Okay. Yeah, I see that version changed. Okay, so the default is 10%. I went with 5. So I'm glad I clicked on that. I wouldn't have even seen that. let's run this. So we create our isolation forest object, and then we fit our model to the training data. So we run our fit function. We have now created an isolation forest model that is trained on our data. Very nice. And we can now run our predict function. So in production, this is what you would be running when new data comes in. So you would fit your model based on your existing data that you have, labeled or unlabeled. Probably want labeled if you're using this in production. And then you would use predict. And predict is what you would run every single time you get new inputs. And that's it. And you'll see, for those that are using LLMs and things like that, you'll see that these type of algorithms are much, much, much faster than those. It's just, the algorithms from the old days, much faster than LLMs. But that's just due to the size and complexity and everything like that. So we run that, and now we can look at our anomalies. We can see which rows are anomalies. Now it only shows us in this 1D version, it only shows us the length count. And if it's an anomaly, but we can see that 105, and I believe, yeah, -1 is an anomaly, 1 is not. So we would see here that this row is an anomaly. This one isn't. This row is an anomaly. This one's an anomaly. This one's an anomaly. This one's an anomaly. And that is it. Now you're probably asking me, Matt, if 18 is an anomaly, why isn't 9? If 105 is an anomaly, why isn't 141? In this specific printed out version, you can't see the other dimension. So that other dimension might be a number that is so far, different or so much of an outlier compared to it that sort of causes, the entire row to be an anomaly. I bet you this 141, which isn't an anomaly, is probably that other value is probably so incredibly in the middle of our sort of variance, the proper the noun count. It's probably like directly on the average of the noun count that it doesn't end up being an anomaly when you sort of aggregate it together. That's one of the things that's interesting about sort of the different dimensions and those type of data sets is you now need to take into account all of the data that's being used, not just a single column of data. You need to remember that there is another column here that affects that score. Anyways, let's take a look at some plots. You will notice, I will say, you will notice that the anomalies, when we just look at this, are generally going to be more off the mean than, like it's going to be very hard to have a number that's, dead smack in the mean and then have the other one be an anomaly. Like, let's say the mean is like, I don't know, 50. 105 is far enough away, 101 is far enough away. This one must be wildly different on the other side. 16 far away, 18 far away. So there has to be some level of it for the other column to, be able to affect it that much to be an anomaly. Anyways, let's run this one. I believe this just gives us a graph. Yeah, so you'll see kind of what I was talking about. So still we are just looking at this on just our X and our Y. We do have query length mapped against the noun count. You can see, of course, that these ones that are way over here end up being anomalies just due to, a high count as well as, being far away on query length. Some of these, just due to them being far away from, let's say the mean is like 40, being far enough away as well as a low enough count. So that is nice. I don't really like the way this looks when we have multiple dimensions, so I do want to take a look at this, which I think does a much better job. Sorry. Much better job of looking at our anomalies. This is a much better graph. This is what you should be using when you look at multiple dimensions. There's also a 3D version of this, which is, of course, what you would want to use if you're 3. So the red are anomalies, the blue are not. And this kind of makes sense, right? This, clearly an anomaly. 0 noun count. It's the only one with a 0 noun count and a really low query length. Done. 4 noun count. That's, look at how many, there's only this many values that are 4, and it's super low on the query length. Here we go as well. 2 for the noun count. That's not that high, but, over 60 query length. That's huge. There's only 2, right? This one, and this one, clear as day anomalies. Very far on the query length, very high on the noun count. Those are clear as day. But you can see that even when we sort of look at each data point as its own, like relative to noun count and query length, you can see that in terms of grouping as well, you can see how they group together. And that's another way to look at the anomaly, right? You got this big group here. You've got a big group here. Everything that kind of falls outside of that, ends up, being an anomaly. So this is probably the best way, and I'm glad we put this one together. This is one of the best ways of looking at this data. It makes it, I think, the clearest when you look at having multiple columns, multiple dimensions. But this is what our data set looks like. So yeah, that is what I have got. The code and everything will be down below, like I said. Let me know what you guys think. Let me know any of the questions that you guys have. I will provide you the data set as well. This is a use case that I absolutely love. Monitoring models and monitoring tools is becoming such a big part of AI. So things like this are very beneficial, and they work really well. I mean, this was a 160 rows, and then we used 20% of it is the test. So we only trained on what, like 128, right? 128 rows, and we were able to get something that fits well. Like I mean, you could make some arguments. Like you could argue this one, although I probably wouldn't. You could argue these, I wouldn't. But I think it worked really well. And imagine when you run it on, 10,000 records or something like that, and your data is labeled. It's just such a great algorithm for this type of work, for anomaly detection, outlier detection. It just works so well. I don't have to play around with some distance algorithm, everything like that. So that is all I've got. Everything will be down below, and I will see you guys next time.